Alright, so we're going to get started. So this is hardware at CuseHacks. So if you haven't already, please be sure to sign up for CuseHacks, happening February 15th to 16th. That's our link right there, cusehacks.github.io. Alright, so basically, just to say real quick, my goal for this presentation is just to make you all aware of like what hardware will be available and to also teach you some basics of circuits. So some of you may not completely understand everything on this spreadsheet, on this presentation, but that's totally okay. It took me years to understand a lot of this, so just please be patient with yourself as well. That's the most important thing. You're not going to learn everything about electrical engineering in an hour. But as long as you learn one new thing, I think my job here is done. Alright, so plus you might get some ideas while watching this presentation, which is hopefully my goal. So the first thing we're going to talk about is just circuit basics. So how many of you have heard voltage before? At least familiar, you know what voltage is. Okay, that's good. So voltage is what makes electric charges move. It is the push that causes charges to move in a wire or other kind of medium. It can also be thought of just how much electrical energy is between 2 points, like a positive and a negative, how you see in this battery. So when you put your battery into a toy or something, the reason why you have that power going into something is because of that positive and negative, because of that voltage. So have you ever noticed if you put a battery backwards, it doesn't work? That's because you need to connect it in the right polarity, which is just the right direction. Does that make sense? Everyone good so far? Okay, good. The next thing is current. So an electric current is a flow of electric charge. So it flows from positive to negative. So this is really important. So whenever you have any kind of voltage supply, whether it be a battery, whether it be a microcontroller, whatever it is, it's always going to flow from positive to negative. So that direction is always going to go in a loop. So we like to call it. And let me know at any time if you have any questions. Feel free. So there's two different types of current, actually. There's alternating current and there's direct current. So alternating current is defined as the flow of charge that changes direction periodically. So if you recognize this, it's more like a sine wave. And that's actually what's outputted from our wall outlets. So our wall outlets give us AC power. It's more commonly used in, industries and houses and office buildings. And then DC is like the basic source, and it's produced by batteries and microcontrollers. But AC is more preferred because it's actually safer, and you can actually deliver way higher voltages with alternating current. But all electronic and computer hardware uses DC to function. So this little cube that your phone comes with so you can charge, that actually converts AC to DC, so your phone can actually charge. So actually, fun fact, if you saw the AC/DC logo in the corner, the band developed the idea for the band's name after their sister saw the initials AC/DC on a sewing machine, and the abbreviation is meaning alternating current, direct current. And the brothers of the band just felt that the name really encapsulated like their energy, and so that's why they went with that, and it just kind of fit their music, very electrified. So that's really, I just kind of wanted to share that because I always saw AC/DC, the band name, and never really understood like why, considering I knew what AC and DC was, but found that out while making this presentation, so I thought I'd like to share. Okay, so we're going to go into our first circuit element. So basically a resistor resists the flow of electricity, just like the name suggests. So the higher the value, the more it's going to resist. Simple as that. And so the less electrical current will actually flow through it. So we are going to use this to control how much electricity flows through the LED, which is actually going to be a thing that I do later on in a couple slides. And in these slides, I also include the units. So the unit of resistance is an ohm, or symbol omega. For current is amps, or A, and for voltage is V, volts. And usually 1 ohm is way too small to even do anything, so we're usually working in the way smaller, the way larger values like kilo ohms and mega ohms, which you can see is times 10 to the 3 or times 10 to the 6. Unlike LEDs, they don't have a direction where they need to go in, So regardless of which way you plug a resistor into your circuit, it's going to work the same way, which is really important. Okay, that's fine. Any questions so far? Am I going too fast, too slow? You can tell me. I can slow down a little. Okay, perfect. Thank you. So a quick thing about resistors, they actually have different values, and the way you tell is based on the color of the resistor. So this little diagram here shows you how you could actually interpret those colors and come up with the resistor value. So depending on which color you have, it correlates directly to a number on all three bands. So if the first one is green, then it's 5. If the second one is a brown, then it's a 1. The third one's a black, it's a 0. And this multiplier is usually like times 1, times 10, times 100. So that's how you know how big it is. So it's a kilo ohm or a mega ohm. And this right here is called the tolerance. Usually you don't have to worry about that too much in your circuit, but what the tolerance is like plus or minus 1%. So resistors are accurate enough to work in circuits, but they're not exactly, 51, 1,000 ohms. It could be 49,999 or 50,001. So you really don't care too much about the tolerance when you're making circuits normally, but it is good to take into account, and they do list them on the resistor. And you can also find this image in a quick Google search. If you just look up resistor color chart, it shows you everything you need to know. There's even apps that you can take a picture of your resistor or type in the colors and it'll tell you the value. So there's a lot of cool resources out there. So this is a basic circuit schematic. So like I introduced, the voltage is your power source. You have your current that's going from positive to negative, and it's going to go through a resistor, which is going to resist that current. So one thing that I do want to note is you never want to connect the positive to the negative without something in between. That's called a short circuit. So you can actually damage your power supply. If it's a battery that has chemical energy, you could actually cause some kind of explosion that way, or some kind of catastrophic thing that you don't want to happen. So in general, a resistor is there just so you can provide some kind of resistance, something that'll stop the electrons from going so fast from point A to point B. This is a cheat sheet just for some circuit formulas. So let's say you want to know what resistor value you need. So you know that you have 5 volts as a power source, and your LED needs 1 amp. So you know that 5 volts over 1 amp is going to equal 5 ohms. So that's basically how you would determine these kinds of things. Again, this is also available on the internet. If you just look up circuit cheat sheets, it's really simple to find. There's a lot of calculators online that'll do it for you as well if you tell them what you have. So don't worry too much. It's also very simple math. It's just one ratio. If you ever did need to do it on your own, you can do it from anywhere. And this is what I want to mention as well. Power, calculated in watts, is probably what you hear about a lot. So when you get power at your home, this is what you're getting. So it's actually a multiplication of how much voltage and how much current you're getting. A lot of the time, it's, for very simple circuits, you don't really need to know, especially if it's just like the simple circuit that I had earlier. Like this, if you wanted to know the power, that's okay, but it's usually in more complicated circuits that you really want to start calculating power, especially in the field of power engineering. But I'm not going to dive into that because that is not beginner at all, and probably one of my least favorite parts of electrical engineering, so not going to touch that. But yeah, so like I said, the power is the electrical energy supply, and the ground, or earth, is a reference point. So that's really important as well. So the power is always going to be the positive, and the ground is the negative. So that's what you see on your battery. It has a power and a ground. And what's really important about ground is that because it's a reference point, that's where the electrons that are flowing will go back to. If it doesn't have anywhere to go back to, your circuit is not going to work. You need to have a closed loop in order to have a circuit. That's just the law of physics when it comes to electronics. Does everything make sense? Good. Speed okay? All right, perfect. So I'm going to be showing you a little bit. If you guys want to step up for this one, I have a couple demos as well to show you. Yeah, come over here. Come, get friendly. I won't bite. I'm trying to see. The camera doesn't pick it up. Come over here. Is that? The camera's frozen. It works? No. Sorry. Just want to make sure that the stream is also seeing everything. So if you want to watch this video later, you can also see what I'm referring to. There it is. Alright, so this is the power supply module that we will be supplying at CuseHacks. So basically you have your plug-in from the wall that'll go into this jack right here. The diagram is also on the slides, so the DC input jack is what I'm referring to. And it actually has different kinds of voltage that it outputs. So you can have either 5 volts or 3.3 volts. Usually I like to use 5 volts, it's just more general, but sometimes when you have more sensitive electronics, you'll want to go with a lower voltage so you don't fry anything. So that's just a very simple, explanation of it. It also has a USB port, so if you had a USB to USB cable and a USB hub, you could also power this module that way. And then you can plug this right into your breadboard, and it would actually power anything that I do on this. That make sense? Okay, good.
Is this like a multi-purpose charge?
Yeah, so you can use this for literally anything. Let me show you what it does when I plug it in. It actually has this little light to indicate that it's turning on. But this you can use for pretty much anything. The way the pins are set up are, you see these male pins. These are called male, and then this is a female. I'll explain that a little more also later. But, you have ground, so G and D usually stands for ground on these kinds of power supplies. You can see it on the image over there as well. So G and D stands for ground, so you would plug in, usually black refers to ground, you would plug in your wire to ground, and that was where your reference point is. And then you plug in either 3.3 volts or 5 volts, whichever you are, you need for the circuit. So here I'll be using 5 volts for my demos today. And you can use this for anything. Really, the breadboard is like the main use for it. I don't really see many other purposes for something like this because it's so small of a voltage source. Like you can't really charge your phone with this. It doesn't have nearly enough power as you need. But a Raspberry Pi or an Arduino, if you're familiar with those, and I'll also be touching on those later if you're not, also has those capabilities as well. They actually have a lot more power because they're more like a computer than just a power supply. So there's a difference in these kinds of things, but we will be supplying microcontrollers as well that do have a little bit more processing power, but these are mainly used for circuit boards, for small circuits. Right, I'm going to try and figure this out as I go. Okay, so that's just a little bit of explanation of the wires I was describing. So this wire right here is the F to M DuPont wire, so female to male, that's what F to M stands for. So the female end is the one that you can plug stuff into. The male end is the one that you plug things into as well. I don't know if I explained that well, but it's there. Yeah, the male ends have the protruding pin. The female ends are inverted, so you plug pins into the female end. And in terms of jumper wires, that's these kinds of wires. So they're actually male to male. So you would use these on the circuit board to connect 2 points. So important that you know the difference between those two. It's also kind of intuitive. If you see this wire and you see you can't plug it into there, you know you're not using the right wire. Or if you're trying to use this wire on your circuit board, you're going to realize you can't plug in on the other end. So the wires are pretty easy. Wires are something that I didn't really think there was that many kinds of. But these are the ones that we'll be providing. They're the ones that really are most important for basics of circuits. And yeah, they're pretty straightforward. It's intuitive in a sense, So a breadboard enables you to prototype circuits. A lot of the times, if you're using an actual product, it's going to be soldered, which is basically like kind of like a metal glue in a sense, where they're connected more permanently. But a breadboard allows you to make edits to your circuit really easily, where I just have to unplug and move it over. I can just start fresh with this and do a whole new circuit. So breadboards are really, really preferred. Sorry, let me go back to...
Can you just say one time what's this like?
Yeah.
This do?
My next slide. You're ahead of the game. No problem. So I explained it there a little bit. So the power rails are this red plus and the minus. So like I said earlier, plus is your supply and the minus is your ground. The way the direction of these circuit boards work, or these breadboards work, are also represented on this slide, but the power rails go this way. So if you were looking at it from this orientation, like it is on this slide, they go horizontal. The same thing with the ground. So there's actually metal under this plastic, which is actually how they connect on the breadboard. So if you have a wire plugged into here, I can basically provide power to any point on this breadboard now from this line. So if I plug in my power supply from here, then I can go here if I wanted to. It'll still have the same power because it's connected this way. Whereas here in the middle aspects, you see that they are oriented a different way. These now are oriented vertically. So that's very important to know. So if I want two wires to be plugged in next to each other, they have to be on the same vertical line, like these are. Does that make sense? If I try to do it next to each other in the horizontal way, they're not going to be connected and nothing's going to happen. That's very important to know. Another thing is these rows right here, these A, B, C, D, E rows, are not connected to the F, G, H, I, J rows. So let's say, let me take a resistor. Remember what those were, right? So if I take a resistor and I plug it in over here, even though it's on the same like line, how I said they were connected, they're not connected now because it's two separate sections of the breadboard. So that's very important to know. That's something to always keep in mind. And it just gives you a little more room to work with. Because once I connect the resistor here, everything I connect on this line, A, B, C, D, or E, is going to be connected to the resistor. And sometimes I don't want that. But sometimes I don't have enough room vertically or horizontally or anything. So that allows me to go into the next one and gives me more space on this to work with. Is everything clear? Makes sense? Okay, good. Okay, so capacitors, I won't be doing a demo on them, but I did want to touch on them because we will be providing these as well. A capacitor is a device that stores electrical energy in an electric field. Don't worry about the electric field, electric energy, just basically think of it kind of like a battery. The only difference is that a battery uses it in the chemical form, sorry. So there's chemicals inside of your battery that's what gives you your power source. Whereas a capacitor, it stores electrons. It doesn't have any chemical anything in it that makes it work. It's just when you charge a capacitor, it's the electrons in it. And then, batteries they provide you very constant power. So if you plug a battery into a toy, it's just going to work the same way until it dies. Whereas a capacitor kind of has more short bursts. It's more susceptible to things like that. So you wouldn't really want to use a capacitor in something like a phone battery because it's not going to be consistent amount of battery normally. Capacitors are also more susceptible to being, when it's discharged, more susceptible to damage that way. Especially the small capacitors, like the ceramic ones that you see, those are pretty weak. So if you use them multiple times, their actual functionality is going to die down a lot faster than a battery would, especially the rechargeable batteries. But yeah, so at CuseHacks, these are the values that we'll be providing. Don't worry too much about it. Don't get stressed with those values. It's really just if you find an idea of a circuit you want to make and you figure out you need capacitors, then you know what values that we're giving you. That's really why I wanted to list out what we have.
I have a question.
Yeah, of course.
So what would you want to use a capacitor for?
So there are cases, I mean, mainly, I actually only ever use them in, like, labs, and for modeling. Like, if you want to see how a capacitor actually discharges, but one application of it is actually a filter. So, you know, you have an audio sound that maybe has some noise in it. You can actually build a filter with just a resistor and a capacitor. It can be a low-pass filter, which only allows low frequencies, or it can be a high-pass filter that only allows high frequencies. And literally all you need is a capacitor and a resistor, and depending on the orientation, if you flip them, they do different things. But all you need is a capacitor and a resistor, and you can make a filter. So that's one application of it. So let's say your project, your idea did involve audio sounds, maybe you had to filter out some noise in it. That is one application of a capacitor that you would want to use. And the way you would actually determine the frequency of that, of what you want to filter out, is based on the resistor and capacitor values. So a lot more on that is online. If you are interested, you can just look up a low-pass filter or high-pass filter, and it'll show you how to construct them with the circuit. So this one I actually do have a demo for. Let me make sure that we are all set here. So a diode is a device with two terminals, but it only allows flow of charge in one direction. So I'm going to demo this a little bit, and bear with me while I build my circuit. So I have my power supply, which I'm going to plug in to the plus rail. And then I'm going to plug in my, I need this one, female to male. I'm going to plug in my ground into the minus rail. Then I want to bring the power into any one of these, it doesn't matter. I'll bring them to any row I need. And then I'm going to put a diode. So this is a diode right here. Really, really small. They're really easy to lose, so you got to keep your eye on them. Trying to make sure that when you refer to this video later, or if you're watching live, you can see what I'm doing as well. So you see that the direction of current flow goes from the anode, the positive, to the cathode. Just like in regular circuits, it goes always from positive to negative. So the cathode is usually denoted by a strip, which in this case is going to be a gray strip on the end. So I'm going to plug it in the right way, and I'm going to try and make an LED light up. So I'm going to plug this into here, which is connected now to my power. Also, convention, always make sure your power supply is turned off when you're building things so you don't fry anything or hurt yourself, because I've gotten shocked a lot of times for not doing that. So I'll move this over to a different row so it's not connected, because I want the loop to close. And I'm also, let's see, am I going to add in a resistor? I'm not. I don't need one. So then, this LED, which I'll talk a little bit about in a second, an LED stands for a light emitting diode. So it's very similar. So the convention, the direction of this matters because of that. So usually the way you can tell is that the longer side is the positive and the shorter side is the negative. So long side is the positive and short side is the negative. So I want it to go from positive to negative. So I will plug my positive side where my diode is, and the negative side can go anywhere else. And then I'm going to finish, I'm going to have to close my loop now, because if I try to turn it on, nothing's going to happen. But now, once I close my loop, it should work. Sometimes you got to finagle with these. So now we have an LED light. So I have made a circuit. So congrats, you just witnessed me making your first circuit. So you see that the diode is in the correct direction, so that's why it's working properly right now. Now let's try to flip the diode to prove, essentially, if that's actually how it works. So once I turn it around, I'm going to make it so it's actually going from negative to positive. You might see the LEDs actually lighting up a very, very, very faintly when I do this. It's because of residual energy, especially from my fingertips. But now I'm going to flip the power supply on, and nothing happens because the diode isn't in the right direction. Simple enough. Everybody understand? Okay, great. So that was our first demo. I have a couple more for you. Hopefully you learned something a little better by visually seeing me build one. Okay. So I already spoke a little bit about LEDs, but I'll go a little bit more in depth. So LEDs, or light emitting diodes, make great indicator lights. They use very little electricity, and they pretty much last forever if you use the right resistor value. The LEDs that we'll be providing, and the one shown, is a 5mm red LED. So the 5mm just refers to the diameter. You can have really, really small ones or really, really big ones, but the ones we're providing are 5mm ones, so I'll focus on those. And usually you'll want to use about 330 ohms at least, just to ensure that you don't burn them out. So that's really the minimum that you want to go with. You can go higher, but it'll just make it dimmer, which I'll actually demonstrate as well. And you cannot directly connect an LED to a battery or voltage source because, again, it has a positive and negative LED, so if you do it backwards, it's not going to turn on, A. And B, if you don't use a resistor to limit or choke the amount of current flowing through it, it will burn out. So I'm going to do a little demo of just LEDs, and I'm actually going to try and make them dimmer and brighter. So I no longer need this for right now. I'm going to take out my diode. Goodbye. Alright, so first things first, we need a resistor. So I'm going to use this resistor that is, I believe, 330 ohms. So this is our minimum. Should be. So from positive, this right here that we had before, this is where our power source is coming from. It's going into the positive. So I want to connect it in the same row. And again, anywhere else is fine as long as it's not in the same area where it's going to be connected again. Then take my positive side, the longer side, and connect that over here. Can everybody see fine? Is everyone good? Okay, you can come behind me too, or over in this side if it'll make it a little easier. I really don't mind. So I have it connected on one side, connect this over here, and then I'm going to close my loop. Alright, so let's verify that I did this right. Turns on. That's great. So we know that we made a proper circuit. Our resistor is making it so our LED is not burnt out. Usually the way you would tell if a resistor or if a LED is burnt out is when you turn on your circuit, if it flashes and turns off. Then you know that LED is useless now, just a piece of metal. So they're really cheap, so if you do end up burning one out, it's not the end of the world. I have like a bunch of bags of LEDs at home for some reason. Like, they're super cheap to find. The only thing is, you know, in the end, you don't want to just waste your resources. So again, we will be giving a limited amount of LEDs at CuseHacks in these hardware kits, so try not to burn them all out, more for our resources as well as yours, but that's just convention. So let me actually try using a higher resistance to see if we can make it dimmer. So this was 330 ohms. Now I'm going to use 1 kilo ohm, which is a lot more than 330. And let's see if that affects our light. Alright, both ends are plugged in. This computer really quick. Make sure it doesn't die on us. Now let's see. Still looks pretty bright, right? Can't really tell the difference. Let's try something that's 10 times higher. So I'm going to try 10 kilo ohms and see what it looks like. Sorry for the silence. I just want to make sure I get this in there. Still pretty bright. It's interesting. Well, usually it'd be dimmer. Maybe it's just a really high power supply. Maybe I need an even higher resistor. The great thing about it is that resistors are also cheap and come in bulk. So if you ever needed anything even higher, they go up to even like 330 kilo ohms, or you know, in the mega ohm range. So you could go higher. Also, FYI, the pile I grabbed this from, it might even just be a bunch of random resistors, because that's usually how EE labs work. So let me try another one, see if we can get anything dimmer. See if that one was actually 10 kilo ohms or not. I could. Well, in theory, it should be dimmer. I'm guessing I don't actually have a 10 kilo ohm in front of me. But yeah, let's check it out real quick. So let's see, our first color is orange, so it's 3. Second color is also orange, 3. This is looking like a 330 kilo ohm right here. Our last one is brown, so it's 1. Yep, 331. Yep, this is a 331 kilo ohm. So it's always good to check to make sure. You might think it's 100, you might think it's 10K like me, and it's not. So that's actually a perfect example of why you always want to be able to check your resistors. But I'm just going to move on for the sake of time. But in general, it's going to get dimmer for the higher resistance because of just the fact that resistors resist current. So less current will actually be able to flow through, less will get to the LED, and won't be as bright. But I want to move on because I have even cooler demos to show you. This one is like the simplest one, not the coolest at all.
How do you know how much voltage is flowing?
Yeah, so usually you'll know, so my power supply, I plugged it into 5 volts, so that's a given. I know that there's 5 volts going through this because that's what I plugged it into. If I were to plug it into 3.3, then you know for sure there's 3.3. What you could also do is, you know, if you ever come across one, there's also a voltmeter. So it's literally like a little device that has 2 little like pins that you can plug in between any 2 points, and it'll tell you how much voltage is going through them. So that's just a device that you can actually find pretty cheap on Amazon, probably like $5–10, depending on like what brand you get. But that's something you could always get if you're ever interested in making circuits at home. And I highly recommend, if you're ever going to be making circuits, to invest in a voltmeter, because you always want to be able to, kind of like how you debug software, you want to be able to debug your circuit. That's literally what we call it as well. So let me move on to the next part. So this one's pretty cool. So this is a button. You know what buttons do. You press them, turn things off, press them, turn things on, usually. Same thing with these push switches, which are basically buttons. And yeah, so this little diagram right there just shows you what happens inside of the button. So when you press it down, it'll connect everything, and when you let go, it actually opens the circuit. So there's like a little lever that opens up and opens the loop, but when you press it down, it'll close the loop. So let's implement that into here so we can actually see what it looks like. Alright, so we already have our LED on there, so that's okay. Actually, let me just show you guys on this one, because it's already made. So I have a couple of things going on here, so let me disconnect everything I'm not using. I'm going to be using this one right now. So this right here is our push switch, just like you see in the image. Looks exactly the same. And the way I have it right now is, this is the positive, this is our plus, our power source, going into our rail. Then it's going into one of the 4 clips that you see on the bottom. So right now it's going into A, and then it's going to run across D, go into our resistor, our LED, and then back through the switch into ground. So let's plug in our power supply into this one and see what happens. So we have our negative goes to negative, positive goes to positive. Alright, let's turn this on and see what happens. So it lights up. Now does someone want to push this button? Go ahead.
Okay.
Press it down. Hold it. See how it turns off?
Yeah.
And let it go. Alright. So, not many, I guess, applications for a button like this one, because it's not the kind where you press it and it just stays off. It's more like you press and it will turn off while you're pressing it, and then when you let go, it stays on. So if you can come up with any ideas of how to implement this in a circuit, please let me know, because I'd love to know what you can actually apply this. But I did just want to show you a little bit of how it actually works for when you do, if you do want to use it. But it's pretty cool pressing the button. Does anyone else want to click it? It's pretty satisfying. When I was building this, yeah. Yeah. Yeah, press it. Go for it. Click it. Makes a satisfying noise, honestly. Yes. All right, guys. Yeah, so that's a push switch. One of the most simple elements, honestly, that I'm going to show you. But again, if you can find a way to implement it, and if you come to CuseHacks with that idea, I'd love to see what you do. So definitely let me know and pull me over to your table so I can see it. All right, so let's move on. We go back to presentation. All right, so this next one is a buzzer. So a buzzer makes a buzzing noise. There are two kinds of buzzers that we'll be providing. Both of them look like the images on the right, on the very right side. And this right here is specifically a passive buzzer. So do you guys remember AC and DC that I taught earlier? That's the difference between an active and a passive buzzer. An active one makes a sound when it has a DC, and a passive one needs an AC signal to work. So you know the difference between an active and a passive if you look under it and you see the little green circuit. If it's a little green circuit, then that's a passive buzzer. If there's nothing under, if it's just black, it's an active one. So I'll be using an active one because this provides us with DC power. I don't have an AC power source, so wish I did, but then I'd have to bring over a big bulky thing, and not very fond of that. But let me show you. We'll make another circuit. Are you guys liking me building circuits with you? Okay, good. I'm hoping it gives you at least a little bit more of a visual of what's going on.
Still trying to figure out how to connect in the positive ones.
Are you still trying to figure out how to connect it? Yeah, it's something that comes with practice as well. And definitely there's, again, the internet's your friend. You can go on YouTube. Any Google search will just show you exactly how to make simple circuits as well if you're ever at home and you ever want to practice. But it comes with practice, really. And breadboards are not the most intuitive thing to use. Definitely it's a learning curve. It took me a while to really understand what I was doing with this. And I've studied electrical engineering for the past 3.5 years. So it really is a learning process, but just be patient with yourself as always. So I already have this buzzer over here connected. I didn't remove the seal because I did not wash it, but it still makes a noise. But you'll see that the seal says, remove seal after washing. I thought that was kind of weird. I didn't know why, but maybe there's some kind of chemical. I don't know. I was always taught not to put anything electrical underwater, so I didn't do it because I didn't want to ruin it. But let's turn off our power supply. Let's disconnect these because we're no longer using the button. And let's now, so we have this power going to here. That's fine. We don't need to move those. And I'm just going to put our positive to now this rail because that's where it's connected here, if you see. So I'm going to move it to this power rail. And then make sure always have ground or else your circuit's not going to work. Alright, so what do you think is going to happen when I turn it on?
It's gonna be a buzzing noise.
Yeah? It's kind of annoying, right?
Or
I don't want to leave it on for too long because it's not very pleasant, but it is a noise. It's a buzzer and it works. And it's very, very simple to wire. You don't need any resistors in between or anything like that. And if you actually use this with something like an Arduino or Raspberry Pi, you can actually control what frequency it outputs. So you can put higher pitches or lower pitches based on what you want it to do. The applications of this is usually in like your laundry, your washing machine. It has a buzzer, right, when it's done? Same technology. So if you ever wanted to use this in your idea, let's say you want an indicator that's not just a visual indicator like an LED, you want a sound indicator, that's when the buzzer would come into play.
Wait, so can you program a breadboard to do anything? Or
No.
No.
So breadboards are pretty dumb.
Okay.
Yeah. It's literally the only thing in this right here is just metal under it, and that's what does the connections. Because metal's a very good conductor. So breadboards are pretty dumb. They're not going to do any coding or anything, but I will talk a little bit about some microcontrollers that we'll be providing that do have those capabilities. All right, let's move on to the next thing. Has everyone at least learned one new thing so far? Okay, that's good. Alright, this one's pretty fun. I actually had fun playing with this one. So this is a photocell. It's a type of cell, and it's used, it's kind of like a light-dependent resistor, so LDR is another way to refer to it. And as the name suggests, the components act just like a resistor, but it is light sensitive. So depending on how much light falls on the top of it, it'll actually change the resistance. And that's the resistance range that is listed right here. So it's 50K in near darkness, and then 500 ohms in bright light. So the brighter it is, the more resistance. So that's set up right here. So that's this. This is a photocell in person. Again, all these components are like super tiny. So I highly recommend being very organized with any hardware you're ever going to use, because it's so easy to lose them. Happens all the time. It's not very fun, especially if it's something really expensive. So definitely keep an eye on them. But the blue LED is going to be what's showing our photocell. So again, I have a positive and negative. I don't want this one to make an annoying sound, so I'm going to disconnect it fully. And now we have this positive and this negative. So again, as always, positive on the pink line to positive, this pink line, and then negative, which is blue, to negative. Now, let's turn it on. So it lights up, right? And now it's light dependent, so let me try and cover it. Do you see it get dimmer? Come over, get close, get close. Oh, let me make sure they're seeing it here on the stream too. Alright, so, do you see it? Here, yeah, it's really easy to tell right there at that angle. Yeah. Come over here, get close and personal. I want to make sure you fully see it, not kind of see it. I need you to see it.
I wasn't sure if it was getting dimmer because your shadow was on the light, so I just...
No, yeah, it's... You can come at an angle too, you see?
Yeah.
It's legit. Yeah, literally, you can tell. Like, any kind of change in light,
That's cool.
it's like, ooh, 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 ooh. Like, it changes. It's pretty cool. And you see that little squiggly line on top? That's what does all that circuitry. I don't know how it works, but it works. But it's pretty cool. And, you can have applications, like, this is really used in, like, sensors, like motion sensors. So if it sees less light, like if a sensor is shooting out a light from you, if there's less light, it means there's something blocking it. So it knows that there's some kind of motion in front of it. So that's just kind of one application of it. Again, if you can figure out how to use it in IDEA, I'm really excited to see that. But let us move on, because I do I have another one? That might be all of my demos, actually. This was the LED that I did on this board also. So I think that's all my demos. If you want to take a seat now. Yeah, I know. It's it can get a little tiring standing up here, but I hope you learned something new. The rest I'm just gonna kind of talk through. I don't have any more demonstrations, but just a little bit more to learn. Okay, so this is kind of similar to the last one that we just saw, but it's actually based on temperature instead of light. So if the room is really hot, it's going to be a higher resistance, as opposed to if the room is really cold, it's going to be lower resistance. I tried to make a demo for that one, but you couldn't really see the difference because I didn't really have a heat source. If I were to have like a blow dryer or something that I could heat it up, you would definitely see a difference. But unfortunately, I didn't have that. I tried using the heat from my fingers, but it wasn't enough. I guess it wasn't different enough than the air. But it's pretty sensitive. But again, it's not really used often. It's usually mostly used in like thermal detection sensors and stuff like that. But yeah, that's a thermistor. It has a pretty funny name. It literally means thermal resistor. They just combined the name, and that's where it came from. A potentiometer is similar. It's like an adjustable resistor. So depending on how you turn the knob, it changes the resistance. And the same way you can use a voltmeter to measure the voltage between, you can also get meters that measure resistance. And that's how you would know exactly how much is going through there. But we will be providing a potentiometer. It doesn't look exactly like that, but it looks really close like that. So a little bit about microcontrollers. We're kind of out of the realm of the breadboard now, so we're going into a little bit more smarter technology. So a microcontroller is basically a small computer on like a single metal oxide semiconductor. Don't worry about what that means. It's just the bare bones. But it's just like an integrated circuit. It's a chip. It's basically like a really small computer. And CuseHacks will be providing Raspberry Pis and Arduino Unos. Unfortunately, it's not actual Pis as much as I would love Raspberry Pis, but that's a really common misconception. Whenever I say Raspberry Pi, they're like the food. Not quite. But this is what they actually look like for Raspberry Pi. It's a low-cost credit card-sized computer, and it plugs into, you can actually plug it into a computer monitor or a TV, and it can use a standard keyboard and mouse. So that's why it has all of those USB outlets. So it's a literal computer. Like you can use it how you could use a computer. And you can learn or use the programs like Scratch and Python. What? Yeah. They're not that expensive actually. You can get the newest model, which is the Raspberry Pi 4. For the cheapest one is I think $35. And it has 1 gigabyte of RAM. And you can get it with 1 gigabyte, 2 gigabytes, or 4 gigabytes, which is kind of insane for this little tiny thing to have. But definitely cheap enough for hobbyists. So if you ever wanted to buy your own, definitely look into it. They have sales all the time too, like depending on where you buy it from, like Amazon. You can get literally 2-day shipping on it. The one thing I will say is if you are looking into a Raspberry Pi, make sure you also get a power supply for your Raspberry Pi because they are sold separately. So the power supplies are about $10, so in total it comes out to about $45. But you can actually program on these things, so they're a little smarter than a breadboard. You can plug them in and you can use Scratch or Python, hence the name Raspberry Pi. And it's capable of doing everything that you'd expect like a desktop computer to do. So you can go on the internet, you can play high-def videos, you can make spreadsheets, you can process Word, like you can even play games on them. It's kind of insane how much processing power these little things have. And again, there's a ton of resources online. I even linked a video in the spreadsheet that you could watch at home if you're interested that literally says everything you can do with a Python, with a Raspberry Pi with Python. And Arduino Uno is very similar, but instead uses an integrated development environment. So you actually have to download a separate like program to write your code into it, and it's a kind of like a simplified version of C++. So depending on your preference, if you're more of a C++ person or more of a Python person, those are really your two options there. We will, I believe, be providing at least a couple of both. So you can definitely, it's first come, first serve. So if you come and you figure out you want to use either of them, definitely come and let us know as soon as possible. But again, it's a very similar microcontroller. It's like a physical programmable circuit board. And, you can actually write and upload computer code to do things autonomously. So if you upload the code onto there and you disconnect it from your computer, it'll run your code without being plugged into your computer. So that's the beauty of that as opposed to a breadboard that just connects things. And as always, the internet is your best friend with anything that involves technology. If at any point you don't know what a piece of hardware does, your best bet is to look it up. You can even do Google image search if you don't even know what it's called. So if you have a resistor in front of you, you're like, what the heck is this? Take a picture of it, do a Google image search, and it'll show up. And, this presentation can also be used to find what the names of the components are. So that's why I included pictures on every slide. And a quick search can give you so much more information. And these are just a couple of circuits and just like tech websites that I found that were really helpful. So buildselectroniccircuits.com, all about circuits. The Dummies website is really good. I love that website because it makes everything super simplified. And there's a subsection for programming electronics components. Same thing with rapid tables and techterms.com. And there's so much more. If you do a quick Google search, you really have to just find what's good for you. So that is the end of my presentation. Thank you for coming.
We actually have some questions in the chat.
Oh, really?
Yeah, so the first one comes from Steve Kelly. He's curious about how the photocell and the Thermistor works.
Yeah, so the photocell actually works because of, there's like, kind of like light sensing technology inside of it. And then it actually measures how many photons are coming in. So photons are basically like light rays, if you want to think about it in a very simplified way. So that's how the photocell works. And the thermistor is definitely a chemical reaction inside of it. So with more heat, the more resistance will come. The potentiometer is your favorite component. Definitely a really good one. Very useful. I actually use that in my junior design project. It was like I wouldn't have a project without it. So it was a really good component. Really easy if you don't know what resistance you really need. You can actually use a potentiometer to kind of determine what works best because it's adjustable. Are you saying my computer interior is actually just a Raspberry Pi? In a way, yeah. Just a very big and complicated version of a Raspberry Pi. It's, a computer obviously has a lot more in it because of the screen and the graphics as well as the RAM and everything, but and the graphics card as well. But a Raspberry Pi in its bare bones, honestly, is a computer. Like it has a processing power enough of it where you can actually do things on it. You can store code and information on it. So it's it's actually advertised as the world's smallest computer, basically. So yes, your computer is basically a large Raspberry Pi.
I think he actually asked Raspberry Pi, as in the food.
Oh yes,
So
actually,
it could actually be made from
real pies.
yes.
I love those too. Let's see.
I think about the quick charger. It says that if the chargers are over 5 volts, it could damage. So you have to be careful with the chargers.
Yeah, always, whenever you want to plug anything in, whether it be a charger or anything, even into your Raspberry Pi, always make sure you know output voltage from your Pi or whatever device you're using, as well as input voltage required for your phone. So that's something that you can actually check online. Do a quick, how much input voltage does an iPhone 7 need, for example, and you could actually check. But you could, in theory, actually charge your phone with a Raspberry Pi because it does output the right voltage. But again, the biggest thing is converting AC to DC power, which is what your block does when you're actually programming, or when you actually plug your charger into a wall, your block converts that. So the great thing about a Raspberry Pi is that it already outputs DC power, so you don't need a block in that sense. Arduino is the better option in my opinion. I agree. I've used Arduino in the past a lot easier to use, and it also, when you download them, you can download a ton of libraries like with the program, the IDE. So it's really simple, and there's a lot more resources for Arduinos. At least the resources are a little less confusing in my opinion. Raspberry Pi is kind of like the step up, a little more sophisticated, especially with all of the plugins that it has on the board. But again, it's really up to your preference. If you never want to touch C or C++ ever, definitely I recommend the Raspberry Pi that we will be providing. Yeah, of course. He said, Steve Kelly said, I'm honored. Thank you for answering my question. Of course. That's what I'm here for. Any questions in the crowd here that I could answer? Yeah. Yeah.
So what are they for? Like what do you
That's a great question. That's a perfect question. So those pins are actually, some of them are power. So just like how we had on our power supply, some of them provide 5 volts or 3.3 volts. There's also one that's ground, of course, because you always need ground. But there's other ones that are actually just programmable pins. So you can actually, in your software, put, like, let's say, output to pin 12, high or low, depending on what you need. And you can actually plug things in, and when your code runs, you can make a certain thing work, or a certain circuit work, or a certain LED light up. But basically, most of those pins, I would say about 3/4 of those pins are programmable pins. So you can make them actually output something depending on what you program it to do. So again, there's tons of tutorials online that will help you do that, but that's a really good question because that's really useful, and that's really what it's used for, So if you want to plug your Raspberry Pi into a circuit, and maybe you want to plug it into multiple circuits, maybe you want certain things to happen depending on what your output is on your code, that's the perfect use for a Raspberry Pi. Any other questions? So, okay, a couple more questions here. From Steve Kelly, is there a way to design your own PCB boards at home, or does that have to be designed in a program like Eagle and then shipped off to a manufacturer? Yes, I would say so, just in my experience, both in the classroom and my internship, that yes, you would have to design it and then ship to a manufacturer. It is, I personally don't really know of any at-home PCB materials or software, or not software, but like physical hardware things that you can make PCBs with. And if there is anything like that, I imagine it'd be probably a lot more expensive than sending it to a manufacturer. But even at my internship, part of my internship this past summer was PCB design, and it's mainly you design at home, send to a manufacturer for them to make it for you, and then they send it back to you so you can actually use. But PCB stands for printed circuit board. So that's basically what their power supply was, what a Raspberry Pi has. On the bottom of it, it's like there's printed wire. So it's not like these big, bulky wires in the way. It's more like kind of embedded inside of the little credit card size chip. And that just makes it obviously a lot cleaner. It's a lot more professional. That's really like everything inside of your computer is a PCB. Almost everything, at least. It's not really, you're not going to find these huge wires inside of your computer, or else you'd probably be mad it was made that way. But yeah, PCBs are very important. All right, yeah, so that's the end of my presentation. If there's no other questions, I do want to emphasize to sign up for CuseHacks if you haven't already. February 15th to 16th, Life Science Atrium here at Syracuse University. Apply at cusehacks.github.io. For any questions or accommodations, you can always reach us at innovateorange@syr.edu. And again, it's going to be a super fun event with food, prizes. You know, it's going to be just awesome that you can come, bring an idea, and make it for 24 hours. And you're going to be surrounded by individuals that, know what they're doing, and you can always ask for help. And there'll be a lot of great workshops there, too. So workshops like these where you can learn something new. Yeah, thank you so much to our viewers on Twitch. I really appreciate it. This is my first time streaming something on Twitch, so thank you for bearing with me. And yeah, of course, definitely anything that you want to learn at home, I highly, highly recommend. The internet, again, is a huge resource. And honestly, like, electrical engineering is such a diverse and great field. So thank you so much. And again, CuseHacks is open to anyone. You don't have to be a Syracuse University student as well. And oh yeah, thank you so much for the follow. But yeah, so I agree. Yeah, we'll be streaming again next week on Thursday. So we have a database workshop next week. Yeah, so we have 2 more workshops. The last one we'll be streaming is next week, which is the database workshop, and it's all about databases. So I'll be there learning something new myself, because I don't really learn that much. And then afterwards, if you are on campus, we will be having a team forming and brainstorming workshop the following week after. So all of these are going to be on Thursdays. And it'll be right before the hackathon. So it'll be 2 days before the hackathon, the Thursday before. It's a team forming and brainstorming. So if you don't have a team, you can come and make one. Or even if you do, come and have some snacks with us and brainstorm your idea there so you're ready for when CuseHacks actually happens. All right, thank you so much for watching on Twitch, and thank you so much for coming in person.